general, you can easily remember this as angular displacement theta is equal to arc length divided by radius, or theta is equal to x by r. Angular acceleration is defined as the ratio of change in angular velocity of the body and the time taken. So here dv by dt is nothing but a, which is equal to r I have as it is I am writing. D omega by dt is nothing but the angular acceleration, it is alpha. Hello everyone, welcome to second session of chapter 7, System of Particles and Rotational Motion. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. Dear children, in the previous session, we have started with the introduction of a system of particles from the rigid body and translational motion. We have learnt rotational motion. We even learnt the position coordinates of system of n number of particles and expressions for them and many more concepts. So in today's session, we are going to study the terms which are related to rotational motion. So what are the important terms that related with rotational motion? So they are like this. It involves angular displacement. So what is angular displacement? It is denoted by the letter theta. So there are several terms that involves in the study of rotational motion, that is angular displacement, angular velocity, which is given by the letter omega, angular acceleration, which is a, and torque, that is tau, and angular momentum L, kinetic energy Ke. So torque is also denoted by tau, and moment of inertia I, radius of gyration capital R. So let us study one by one in detail. So first one we have angular displacement, theta. So what is angular displacement? It is denoted by theta. It is nothing but the angle subtended at the center by an arc of the circle. See, if this is the center, this is arc. The angle subtended at the center by an arc of the circle. So it is defined as the ratio of arc length of the circle to the radius of the circle. So what is the arc length? It is x. What is radius? R. So theta is nothing but the ratio of arc length that is travelled by a particle which is going in a circular path to the radius. So theta is equal to x divided by r. So in general, you can easily remember this as angular displacement theta is equal to arc length divided by radius, or theta is equal to x by r. So let us move on to the next term, that is angular velocity. What is angular velocity? We know what is velocity. It is nothing but rate of change of displacement. So angular velocity also we can explain or we can define in the same manner. It is defined as the ratio of angular displacement of the body to the time taken. As we all know, velocity is nothing but displacement divided by time. We are talking about angular velocity. It is nothing but angular displacement divided by time. So angular velocity is given by omega. Angular displacement is theta divided by time. So omega is equal to theta divided by time, or even we can represent this as omega is equal to d theta divided by d time. So next we have angular acceleration. What is acceleration? We know rate of change of velocity is acceleration generally. So angular acceleration is defined as the ratio of change in angular velocity of the body and the time taken. As I told you, generally acceleration is velocity by time. So we are talking about angular acceleration. It is nothing but change in angular velocity. Change in angular velocity. When can we say the angular velocity is changing? By taking the difference between the final angular velocity and initial angular velocity. So change in angular velocity can be represented as final angular velocity minus initial angular velocity divided by time. We know angular velocity is given by the letter omega. So we have change in angular velocity. That is why final angular velocity, that is omega f minus initial angular velocity divided by time. This is the expression for angular acceleration. So far we have studied angular displacement, angular velocity and angular acceleration. So let us now derive the relation between linear acceleration and angular acceleration. So, we have already derived the expression between linear velocity and angular velocity, that is v is equal to r omega. Let us now derive the relation between linear acceleration and angular acceleration. So, the relation between linear velocity and angular velocity is given by, as I already mentioned, v is equal to r omega. So, now differentiating this expression with respect to time, that is dv divided by dt, which means we are differentiating velocity with respect to time. We get dv by dt, which is equal to, radius remains constant in a circular motion, so r into d omega divided by dt. This is my equation 1. But the linear acceleration is given by rate of change of velocity, that is dv divided by dt, and angular acceleration is nothing but d omega divided by dt. What is d omega? It is change in angular velocity. So, alpha is equal to d omega divided by dt. So, here dv by dt is nothing but a, which is equal to r I have, as it is I am writing, d omega by dt is nothing but the angular acceleration, it is alpha. A is equal to r alpha is the relation between linear acceleration and angular acceleration. Now, let us move on to the another important term, that is angular momentum. So, angular momentum is denoted by a letter L. How to define that? Angular momentum of a body is defined as the product of linear momentum, that is P, and the perpendicular distance of the body from the axis of rotation. The perpendicular distance of the body from the axis of rotation is given by the letter R. So, angular momentum is the product of linear momentum and the perpendicular distance of a body from the axis of rotation. So, in expression we can represent the same as L is equal to P into R, where P is the linear momentum, R is the perpendicular distance between the axis of rotation. So, now let us write the expression for linear momentum of system of particles. So, in this we have to show that the total linear momentum of the system of particle is constant. So, when does this total linear momentum of the system of particle is constant? When there is a zero external force, or we can say when the total external force on the system is zero, then the total momentum or total linear momentum of a system becomes constant. So, we have to prove that. So, to prove that, let us consider a system of n particles. We have a system in which n number of particles are present, whose masses are given by m1, m2, m3 and mn up to mn, and the velocities of those bodies are v1, v2, v3 and so on up to vn respectively. For system of n particles, the linear momentum of the system is equal to vector sum of linear momenta of all individual particles. We all know that a system is having n number of particles. So, each particle of mass m1, m2, m3 and so on up to mn, which are having a velocities v1, v2, v3 and so on up to vn respectively. So, for a system of particles, the linear momentum of the system is equal to the vector sum of linear momenta of all individual particles. So, we can represent that in expression as P equals, what is this P? It is nothing but the linear momentum of a system. So, linear momentum of system is equal to the vector sum of, you can observe here, the vector sum of linear momenta of all individual particles. Since we have considered n number of particles, we have to represent this expression as P1, P2, P3 and so on up to Pn. But what is P? P is nothing but momentum. So, momentum is linear momentum, that is the product of mass and velocity. I have P1, P2, P3 and so on. So, I can represent this as the product of mass and velocity, that is m1 v1. Since v is a vector, I have to represent it with the vector form, plus m2 v2 plus m3 v3 and so on up to mn vn. But what is this together? It gives us the sum of all the moment of inertia of all the individual particles. So, we can write it as P is equal to mv. That is my equation 3. Here in this expression, P is the linear momentum of a body, m is the mass of a body and v is the linear velocity of the body. So let us differentiate this equation 3 with respect to time. So by applying a product rule, we can represent this as dp divided by dt. We are differentiating both sides of this equation with respect to time. So differentiating this, what I'll get? D by dt of p, which is equal to the mass of a system of particle, or mass of each particle remains constant, only the velocity changes. So I can write it as d by dt of v. But what is d by dt of v? D by dt of v is nothing but rate of change of velocity, which is nothing but acceleration. So this expression becomes dp divided by dt, which is equal to m into, this entire term is nothing but acceleration. So I can write it as ma. But what is the ma? We know for the expression F is equal to product of mass into acceleration. So I can write it as dp divided by dt is equal to F, that is force external. That's our next equation. So this above equation is nothing but the Newton's second law. Newton's second law says that the rate of change of momentum is equal to the net force acts on a system. So this expression or the above equation is the Newton's second law of motion extended to system of particles. We are applying this Newton's second law of motion in the study of system of particles. What if this external force is 0? If this term becomes 0, we will get dp by dt is equal to 0, which means the total momentum of a system remains constant. So next, the very important another derivation we have to derive, the relation between torque and angular momentum of a particle. Basically, what is torque? So it is derived from a Latin word which means twist. So torque is basically a twisting force, a force which is responsible for rotation. So we can say it as a twisting force. So we have to derive a relation between the torque and the angular momentum of a body. So angular momentum is nothing but the product of linear momentum and the perpendicular distance between the object and the axis of rotation, and it is given by L is equal to P into R. So where L is the cross product of P and R, which is nothing but the angular momentum of a particle, P is the linear momentum and R is a radius vector. So if the body is moving in a circular orbit, rotational motion if it is having, so it will be changing its position from one point to another point and keeping one axis of rotation. So this axis of rotation, I'll take it as R, the radius, and this will be the perpendicular distance between the body and the axis of rotation. So it is given by L is equal to P into R. So now differentiating equation 1 with respect to time, again by applying the product rule. So we have the equation 1, that is L is equal to P into R. So differentiate this with respect to time. So we will get d by dt of L, which is equal to d by dt of P into R. So we'll get this equation. Now by applying product rule, keeping one term constant, differentiating the other term, we'll get P dl by dt is equal to vector P into dr by dt plus, keeping R constant, differentiating P, will get R into dp divided by dt. That's my equation 2. But what is this dr by dt? Rate of change of position, which gives us velocity. So v is the velocity of the particle. dr by dt gives us v. What is dp divided by dt? It is from Newton's second law, F. So I can replace these terms. So as I told, dp by dt is equal to force from Newton's second law. We can replace these terms in the above equation and we will get dl by dt, which is equal to p into v plus, I already have R here, dp by dt is nothing but F. So I can replace them with V and F and we'll get P into V plus R into F. But what is P? It is M into V. Again I replace P with M into V and I'll get dl by dt is equal to M into V into V, already we have here, plus R into F. We are representing all the terms here with a vector notation since they have got both magnitude and direction. Now the product of two vectors same vectors is equal to 0, the cross product of two parallel vectors will consider them and it will be equal to 0, and this term will be equal to 0. V cross V equals 0, which is again multiplied with m. So the entire term will become 0 and we will get R into F, and hence the final expression dl by dt is equal to R into F. But what is R into F? It is nothing but the torque. Torque is denoted by tau. It is nothing but the product of force and the perpendicular distance between the object and the axis of rotation. So the cross product of R and F is nothing but tau. So that is what we have to prove, that is the relation between torque and the angular momentum of a particle. It is given by tau is equal to dl divided by dt in a vector form. So we are discussing about the terms which are related to rotational motion, in which we have the another term importantly, that is moment of inertia of a particle. So how to write the statement or the definition of moment of inertia of a particle? It is so simple. By just remembering the expression, we can explain what is moment of inertia of a particle. So the moment of inertia of a particle about an axis of rotation is equal to the product of its mass and the square of the perpendicular distance between the particle and axis of rotation. So if any body is having moment of inertia, it can be defined as the product of the mass of a body and the square of the perpendicular distance between particle and the axis of rotation, that is I is equal to mr square. What is I there? Moment of inertia of a particle. What is m? It's a mass of a particle, and r is nothing but the perpendicular distance. So it is given by I is equal to mr square. Moment of inertia of any body, which is equal to the product of mass of that body and the square of the perpendicular distance between the body and the axis of rotation. By just remembering the expression I is equal to mr square, we can explain what is moment of inertia of a particle. So in the next and the last term which is related to rotational motion is radius of gyration. It is denoted by a letter R. What is the meaning of radius of gyration? How to define it? It is nothing but the radius of gyration of a body about an axis is defined as the perpendicular distance. You can observe the perpendicular distance from the axis of rotation and the point where the entire mass of the body is assumed to be concentrated. It is the perpendicular distance from the axis of rotation. So this is the axis of rotation from here to here. The perpendicular distance from the axis of rotation to the point where the entire mass of the body is supposed to be concentrated. We'll call it as radius of gyration. So in today's session, we have learnt about the terms which are involved in the study of rotational motion, and also we have studied about the relation between these terms, how they are related with one another. In the next session, we'll come up with some more interesting concepts. Until then, keep learning all of you. See you all in the next session. Thank you.